Hello. In this video, we're going to be looking at some properties of functions. We're going to start off with two special properties of functions. Functions can be given this special name, even or odd functions. The advantage to classifying them in this way is that if you have an even or an odd function, if you can plot one part of the graph, you automatically have the part on the other side of the x-axis, on the y-axis. So that's really nice here. You'll be encountering these functions if you go further on to math. So college algebra is a good place to start with these. So let's look at the definitions and then also look at these graphically. A function is said to be an even function if its graph is symmetric with respect to the y-axis. What that means algebraically is if I plug in negative x for the function, then that's going to give me the same y value as if I plugged in positive x. So algebraically, what that means, here is a good even function. If I plug in some value of negative x, and get a y value here. If I plug in that positive x, I'm going to get the same y value here for all values of x, So what that means is f of x is equal to f of minus x for all values of x. So we can go ahead and look at this two different ways. You might be asked to just look at that function and tell if it's an even or an odd function. We haven't really looked at odd functions yet. So this one must be even or neither. But this does have symmetry with respect to the y-axis. So it is even. What that means is if I put sort of a ruler or something on the y-axis, then the graph on the left would look exactly the same as it does on the right. And it does. So it's really a reflection of the graph about the y-axis. So here's my y-axis, and my function has total symmetry with respect to the y-axis. So y equals x squared plus 2 is symmetric with respect to the y-axis. And that means it's an even function. That's how we would look at it geometrically. Algebraically, we would say, okay, our function is f of x is equal to x squared plus 2. So if I evaluate f of minus x, I plug in negative x wherever I see an x in my function, I would have negative x squared. And then that would be negative 1 squared times x squared plus 2. Negative 1 times negative 1 is just 1. When I simplify, I get x squared plus 2. So if that reduces to exactly the same thing as the function was before, then we know that this is equal to exactly f of x. So when I plug in negative x for the input, if I compute that y value to be exactly the y value, when I would plug in positive x, so I get the same function back, we know that that's even. So this is how we would algebraically check that it's an even function. Now notice that a function is odd if its graph is symmetric with respect to the origin. So that's symmetric with respect to a point. This one is an odd function here. It's symmetric with respect to that origin point. And so what that means is if I plug in negative x, any sort of negative x, and compute the function value, then I should get the opposite of the value if I plugged in that positive x. So this should be up exactly the same amount as my f of negative x was down for all of those values there. So we can say that y equals x cubed is symmetric with respect to the origin if we're looking at things geometrically. Therefore, it is an odd function. Another way to look at this sort of geometrically is if we flip the function over the y-axis, we would have something like this. And then if we flip the function about the x-axis, get it in there, we would have the same function. So it'd lay right on top of each other. So odd symmetry through this 0.00 would be flipping about both axes. So now, if I want to prove that algebraically, I can take f of negative x. So here's my function now. F of x is equal to x cubed. So I'll have f of negative x. I plug in a negative x wherever I see x. So that's negative x cubed. That's going to be equal to -1 cubed times x cubed. When I simplify -1 cubed, that's -1 times -1 times -1. That's a -1 times x cubed, or the opposite of our original function. So notice our original function here was x cubed. This is the opposite of that function. So if we have f of negative x is equal to negative f of x for all x, then we've just proved algebraically that that's going to be an odd function. Now, if you have a function or a graph that doesn't exhibit these symmetries, or when you plug in negative x, we can't transform it into f of x or negative f of x, then it's not going to have either of these symmetries. But you can hopefully see where this would help. If I could plot part of this function, if I know it's an odd function, the other part on the other side would be flipped about the y and the x-axis, and you would be able to plot that second point for free, essentially. Similarly up here, I plot one point, one part, and then I flip it about this y-axis, and I plot that second part of the function. Right, hope this has helped.